All right, today we're going to talk about reactions that happen in solution. In this case, this is a double displacement reaction because I'm taking lead 2. That means the charge on lead is 2. Nitrate is NO3 with a charge of -1. So this would be the formula for lead 2 nitrate. Potassium sulfide would be K2S. These are both compounds. This is a double displacement reaction. And when you have double displacement reactions, you have two different possibilities for a reaction to happen. You either can form a solid or you can form water. If you don't form a solid or form water or form a gas, it's not really a chemical reaction. So I'm going to try to draw a picture for you of what's going on here. We've got ions. Let's say that we're going to draw nitrate like such. This is going to represent NO3 -1. Let's draw lead, red. Let's draw potassium, green. And let's draw sulfide like such. So these are the colors that I'm going to use to represent the individual ions because both of these compounds are soluble. What that means is when you put them in solution, they will seemingly disappear, but they're not disappearing. They're doing what's called dissolving. So that means that for every one lead that I draw in solution, we're going to make it nice and simple. There'll be 2 nitrates. So I have 5 leads. That means that there's going to be 2 nitrate ions for every one, like such. So when they're together, they're locked in when they're in a solid. So ionic compounds actually have very high melting points and very high boiling points. They are locked into rigid crystal lattices, and they are called formula units. And the reason is because it doesn't matter if you consider lead nitrate to be this. That's one piece of lead nitrate, but it's the same as this piece of one lead nitrate. So we don't consider them separate like molecules because they're individual ions locked into a rigid crystal lattice. We call them formula units to represent one piece of this ionic compound. Now I'm going to go over and do the same thing with potassiums. There's going to be 2 potassiums for every 1 sulfide. So again, when these were solids, they had high melting points, high boiling points. And when you put them into water, they do not melt. They do not change states of matter. What they do is they dissolve. So it's kind of confusing because it looks like they disappear, but really what they're doing is they're separating. And I'm going to have you watch some videos, which is pictorials of the ions separating. So they're now ions floating around in solution, and their state of matter is aqueous now. So they went from solids. All ionic compounds are solids at room temperature. When you put them into solution, they will dissolve and they will be aqueous. So after you put them into the same container together, what's going to happen is that the lead and the sulfide are going to find each other. And when they find each other, there's going to be a chemical reaction because they are not soluble. That lead 2 sulfide is not soluble in solution. So these 2 guys are going to fall to the bottom of the container, and they're not going to be ions anymore. They're going to be what's called a precipitate. The other ions would be the nitrate ions and the potassium ions are still going to be floating around in solution. So notice all of the lead and all of the sulfur, as long as we add them in the right ratio, will form a solid that's going to be lead 2 sulfide. So all of my lead and all of my sulfur are going to be down at the bottom, chemically combined with each other as a solid. Solids that form precipitates, this is called a precipitate reaction, are not considered part of the solution. So in the solution, all we have now is potassium nitrate, as long as we've added them in the right stoichiometric ratio. So the full chemical reaction here is written like this: lead nitrate plus potassium sulfide will switch places and form potassium nitrate and lead 2 sulfide. And that's going to form a solid. I'll balance this like such. So lead was plus 2 ions floating around solution and now is part of a solid. Nitrate was aqueous ions floating around in solution on the reactant side, and they're aqueous ions floating around in solution on the product side. Those did not change, so they are considered spectator ions. Potassium was aqueous plus 1 ions floating around solution on the reactant side, and is aqueous plus 1 ions floating around in solution on the product side. Also did not change, are spectator ions. So here's what we do. Anytime you have an aqueous solution that is a ionic compound or a strong acid, strong acids and ionic compounds are the only ones that we can break up when they're followed by AQ. So what that means is, I'm going to draw the total molecular equation for this chemical reaction is up here, and then I'm going to turn that into what we call a complete ionic reaction. And what that means is I'm going to split them up into the ions. The subscripts and the coefficients are multipliers. So my subscripts become coefficients for the ions. Remember, I only break up strong acids and ionic compounds when they're followed by AQ. So PB, anything that's followed by solid, liquid, or gas, you just rewrite it as is. Now I'm looking for things that do not change. So anything that is exactly the same on the reactant side as it is on the product side are not really reacting. Those are called spectator ions, and they are left out of the net ionic equation. So my net ionic equation becomes what's left after I cancel out my spectator ions. So my net ionic equation is going to describe only the chemical reaction that is happening and nothing else. And this is the net ionic equation that I constructed from the molecular equation up above.